Hi there, this is part 2 of the repair and test of the Marconi TF2331 distortion factor meter. In part 1 I got the device working again. If you have not watched that video, I suggest you do that first before continuing with this one. If you recall, it turned out that the original analog meter with its 0 to 10 and 0 to 3 scales was not working properly anymore, and any attempts to repair it failed. I had to replace it with a new generic 100 microamp meter. While that worked, lots of people suggested to add the missing scale to the new meter, and this is the first job in this video. I started by removing the cover, which is thankfully really easy with this meter and can be done from the front by removing 2 screws. This reveals that the scale itself is held by 2 small screws, which I also removed. Once that's done, I can slide the scale carefully out, avoiding touching the needle. With the scale out, there are a couple of options. Traditionally, people have used Indian ink, ruler and compass and/or lettering templates to draw new or additional scales directly on top of the original one. That is of course risky in that it's very easy to mess up, and then you've lost the original scale. Instead, I'm planning to make a new scale sheet on the computer, print it out, laminate it for strength, and then mount my new scale instead of the original. That way I can always go back if something went wrong. Making the scale takes hours, and I'm just showing the principle. As my main PC is running Linux, I'm using the free software LibreOffice Draw, which is also available for Windows, but other programs can be used as long as they support layering. Also, I'm not saying you have to do it this way, just that's the way I did it. Feel free to experiment. The first step is to load the photo image of the scale into the drawing program. I created a background layer called Picture for that. I measured the width and height of the original and created a bluish rectangle of that size, making it half transparent. This allows me to scale the photo image until it fits my rectangle exactly. Next, the original scale is a 90-degree segment of a circle. I created 3 helper lines, one vertical one and then 2 copies of the vertical one, but one rotated 45 degrees to the left and the other 45 degrees to the right. For better visibility, I choose orange as a color. By selecting the 3 lines as a group and shifting them up or down, you can make them simultaneously match the most left, right and center scale marking on the photo. At this position, the point where the 3 lines intersect is the turning point of the needle, and I can use that to create a circle segment that matches the original scale exactly. All I now have to do is make a copy of the center line and then rotate it to create a scale marking, and repeat this process 50 times. In LibreOffice Draw, you must use the position and size window for that, which you get by pressing F4. In that window you can select the rotation point to be at the center bottom and type the angle into the box. To recreate the original scale markings, 50 copies and rotates are needed because the original scale has markings for 0, 2, 4, 6 to 100. To get the value of each angle, I use the quick spreadsheet. In column A we have the desired markings from 0 to 10. The most left marking for 0 corresponds in my drawing program to 315 degrees and the most right one for 10 to 225 degrees, which is of course 315 minus 90 degrees. The center marking corresponds to the value of 5, which is an exact vertical line of 270 degrees. Since the arc is 90 degrees, if I make 100 markings, each marking would be 90 over 100 or 0.9 degrees rotated more than the previous one. But since I only want every second marking, the rotation is 1.8 degrees. Hence, starting with 225, every marking is 1.8 degrees further than the previous one. I made thicker lines for the markers representing 0, 1, 2, 3 or 10, 20, 30 on the original photo, and shorter, thinner lines for the values in between. This is just done afterwards by selecting the right line and changing its width. With this all done, I changed the line color to black and added new labels which appear a bit blurry because they are on top of the original ones shining through from the photo background. Now I simply created some solid fill shapes to cover the lines that I don't want to see. Once the filled colors of the blue segment and the yellow rectangles are changed to white and the yellow rectangle is shifted downwards, all unwanted lines are covered up. This is the final scale, having both a 10 scale and a 3 scale. The 3 scale is done using the same process, which is extremely tedious. It occurred to me that most people would rather keep the original 10 scale and simply add a 3 scale instead of making two completely new scales as I did here. I decided to show how this could be done and in the end actually use that scale instead of this one. We can reuse the original 0 to 100 scale, which saves a lot of work. If you rather have it go from 0 to 10, you could create new labels or add decimal points, for example 6.0 instead of 60. I did not bother with that. Since this approach shows the image of the original, it should only be used if the original scale is without scratches and other defects. It's also important to get a photo with good contrast. And then enhance it further to the point of a black and white image, because if the background has uniformly the same color, it makes hiding unwanted parts of the drawing with filled shapes a lot easier. The rest follows the same principle as discussed earlier. In this case, I used the orange horizontal line to help me scale the photo, and you can see the 3-line method to find the rotating point of the needle. Since I want to reuse the original scale for 0 to 10, I only need to make a new 0 to 3 scale below. The calculation of the necessary angles for the 0 to 3 scale is a bit tricky. We know that 0 matches the 0 to 10 scale and corresponds to 315 degrees. By carefully measuring the original Marconi scale and a bit try and error, I determined that the value of 3 corresponds to 229.3 degrees on my new meter. This means the whole scale covers 89.7 degrees. Each angle for the in-between scale points can then be calculated, ranging from 315 degrees for 0 to 286.43 degrees for 1, 257.87 degrees for 2, and finally 229.3 degrees for 3. Again, covering up the unwanted lines with filled shapes produces the final scale. I added a marker for the cull position as well. I printed both scales and laminated them. I measured that the thickness of the laminated scale is still less than the original scale, which uses a thin sheet of metal. Initially, installing the new scale turned out to be tricky because it warped when tightening the screws. The reason was that I punched the screw holes a little too tight. That was easily fixed and the new scale did not cause any further issues. The new meter showing 10 millivolts. The camera is slightly offset. Seen from the front, the needle is right on the 100 marker. Switching to the 30 millivolt range shows the meter going to the 1 on the new 3 scale as it should. And selecting cull brings the needle right to the newly added cull mark. Having a new scale is all well and good, and the voltmeter part seems reasonably accurate. The big question is, however, if the TF2331 shows correct values for distortion. To its credit, the manual has a long section on sources of error, nearly all of which are related to the fact that the meter circuit in the TF2331 is only averaging and not true RMS. The section ends with this statement I put in the box. Basically, if you have a true RMS capable meter, probably a rarity when the TF2331 came out, connect it to the output socket and use it instead. The output voltage follows, of course, the range switch. That is, selecting, for example, a 10 times higher range reduces the output voltage by a factor of 10. The problem is that the absolute value the output is capable of is not defined and hovers in the area of 150 to 190 millivolts. This means one cannot use the 1 volt ref level, and therefore the manual suggests to do it at 100 millivolts. I have long thought about the meaning of the and the other scale that corresponds to the percent setting of the meter range selector. No other information in the manual and no helpful example on how to interpret the reading of an external meter. Which range switch am I supposed to use, the external meter or the TF2331's? And what does correspond mean? The 100 millivolt setting already corresponds to 10% THD, so surely that can't be right. I finally concluded that 1 volt corresponds to 100 millivolt when using this method and 100% THD. So when the external meter goes to its 30 millivolt range, that is the same as 300 millivolts on the internal meter or 30% THD. 10 millivolt range external means 10% THD, and so on. As a test case, I'm using this 1 kHz sine wave sent through a little audio amp. The volume is so high that the output is visibly clipped. First, going through the normal distortion measurement steps, the reference level is 1 volt. To speed things up, I have already tuned the filter, so I don't need to do that again. Just 2 clicks on the range switch from 100% to 30% to 10% is all it takes. This means the full scale value is 10% THD and the needle is somewhere around 5.4%. For simplicity, I'm trying to use a modern multimeter capable of True RMS connected to the output. First job is to reduce the reference level to 100 millivolts. Ignore the reading on the analog meter, as in THD mode the meter is not showing actual voltage. When suppressing the fundamental, the reading drops to slightly above 6 millivolts. Since the fluke is auto-ranging, we have to imagine the manual ranging that would have taken place in an older meter. From 100 millivolts or 10% to 30 millivolts or 30% to 10 millivolts or 10%. Clearly, 6 millivolts is more than the next step of 3 millivolts or 3%, so 6 millivolts from the fluke corresponds to 6% THD. That is reasonably close to the 5.4% we measured earlier. A problem with this method appears when measuring smaller distortions. Here's the same sine wave and the same amplifier, but now the clipping is much reduced, but not completely. I purposely left a little flatness, which you can best see at the peak of the positive half of the sine wave. Going through the same steps of the standard measuring process using 1 volt as a reference, I can do 2 additional range changes compared to the previous case where 10% was the lowest range. Now the full scale range is 1% and the needle shows just a tad below 0.7% distortion. Repeating the test with the fluke, first setting the 100 millivolt reference level, suppressing the fundamental reduces the value to between 1.5 and 1.6 millivolts. Range-wise, that means just one additional step from before, namely to 3 millivolts or 3%. And that means 1.5 THD, about twice as much compared with the standard, which was 0.7%. I found this getting worse the smaller the distortion values are. The problem is the noise in the output signal that prevents any readouts below 1 millivolts. It seems that the built-in meter is far less affected by this. And yes, I'm aware that modern multimeters cannot measure such small AC voltages with any degree of accuracy according to their specs. For the fluke, the minimum AC voltage has to be greater than 5% of the range, in this case 2.5 millivolts, to meet its accuracy claims. But as often, the meters are generally better than their specs. And to prove the point, here's the same measurement using the Dana 9300. This is a true RMS meter that can go down to 100 microvolts full range. First the 100 millivolt reference, then the suppression of the fundamental, and now the ranging. 30%, 10%, 3%, and there you have it, still 1.7 THD. Even when I short circuit the input, I get almost 1.3 millivolt noise on the output on all ranges except the lowest 3 millivolt and 1 millivolt range, where it increases to about 6 to 7 millivolts. Even the analog meter shows a small deflection, but that would be about 0.04 millivolt. I would be curious to learn from other TF2331 users if they see similar issues or if I have to start looking for noisy components in mine. In another attempt at verifying the TF2331, I looked at the definition of the distortion factor. The manual explains that there are 2 different ways of measuring it. The much harder to measure method is dividing the total signal with the fundamental filtered out by just the voltage of the fundamental. The other way is what the TF2331 uses, which is dividing the total signal with the fundamental filtered out by the total signal. This method has the problem that it causes an increasing error the higher distortion, but since one hopefully cares more about low distortion, that is acceptable. Anyway, these definitions allow a theoretical calculation of the distortion factor if the overall signal shape can be mathematically defined. But this gets very complicated, so I decided to try determining distortion using simulation in a spreadsheet instead. I'm using LibreOffice Calc, but Excel works the same way. The method is rather straightforward. I have in column A phase angle going in 1 degree steps from 0 to 720 degrees, that is 2 periods of 360 degrees. Column B is the sign of the angle and I call it the fundamental. Columns C, D, E, F and G are the first 5 harmonics. In this case, column C has 3 times the frequency of the fundamental but only 1/3 of the amplitude. Column D is 5 times the frequency with 1/5 of the amplitude, and so on to G, which is 11 times faster than the fundamental but only 1/11 of the amplitude. Column H, which I call sum, is simply row by row the sum of the fundamental of column B and the 5 harmonic columns, while column I is the same but without adding the fundamental column B. I call it filtered. On the right you see a plot of the sum and filtered columns. If you know the Fourier series for rectangular signals, it will come at no surprise that the yellow sum signal resembles a square wave, and it would be a perfect one if I bothered to add more harmonic columns to the spreadsheet. The blue filtered signal is what remains without the fundamental. It is now easy to calculate the distortion factor using the first method I call THDF, and the second method used by the TF2331 I call THDR. As expected, 40% THDR is starting noticeably to lag behind THDF, but still in the same ballpark. The gist of all this is if I feed a rectangle signal into the TF2331, I should measure a distortion of around 40%. After setting the reference level and then rejecting the fundamental, the result is already on the meter. I had tuned the filter off camera. In this case, full scale is 100% and the value shown is about 33%, not quite the 40% for my simulation. The scope shows the input waveform in yellow and the output in blue. The output signal shape closely resembles the prediction of my simulation. It also offers an explanation why the reading is so low. The signal is certainly not sinusoidal, and the TF2331 with its averaging meter introduces an additional error. Let's see what a proper RMS voltmeter would show. This has again to be done at 100 mV reference level. When the fundamental is suppressed, the output goes down to a tad above 0.4, meaning 40%, which is what the simulation predicted. The slight difference is caused by my simulation using only the first 5 harmonics, while this measurement of course includes an infinite number of harmonics and noise. A more extreme case in terms of harmonics is a saw-shaped signal. The expected waveform based on 5 harmonics is shown on the right. The predicted THDR is about 56 to 57%, which is now quite a bit lower than the THDF, which should be 68%. Let's see what the TF2331 makes of it. After setting the reference level and then rejecting the fundamental, the result is very close to 50%. The blue trace on the scope image shows the waveform closely resembling the predicted one from the simulation. And using a True RMS meter on the output signal shows a THD of 60%, which, taking the limitations of my simulation into account, agrees reasonably well with the prediction of 56 to 57%. While the previous examples were based on Fourier series of well-known waveforms, which generally have a pretty high distortion factor, I wanted to try something different for a prediction of a low THD. Here's a fundamental and just one harmonic at 10 times the fundamental with 1/10 of the amplitude. The predicted blue trace is of course just the harmonic itself. The predicted THDR and THDF closely match at about 10%. To create this wave, I added, through capacitors, a 1 kHz sine wave at 3 volts peak to peak to a 10 kHz sine wave with 0.3 volts peak to peak. The measured THDR using a TF2331 is only 6.4%. And the measurement using the external RMS meter is quite close to the internal measurement with just under 7%. That the values are close is kind of what I expected, because the resulting wave after removing the fundamental is just a sine wave suitable for an averaging meter. The waveform of both the input and output signal look right, and the blue signal is indeed a sine wave. I guess that my crude way of combining the signals may be to blame. Just a tiny difference in amplitude, for example from the capacitors, could cause the difference between 10% and 6.4 or 7%. Without a second THD meter that you can trust, it's very difficult to establish how accurate the TF2331 is. I think I've established that it works and doing the right thing. As to absolute accuracy, I think I just leave this question for now. The main thing for me is that, for example, in aligning amplifiers or oscillators, lower THD is better, and determining that is something that TF2331 can certainly do easily. If you like my videos, don't forget to subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.